Hi students, in this video we are going to cover the illumination of light. First, let's discover the nature of light. Physicians have studied light for centuries, finding that it sometimes behaves as a particle and sometimes it behaves as a wave. Actually, both are correct. In some processes like reflection and rectilinear propagation, it behaves like a particle, but in some processes like dispersion of light into colors through prism, it behaves like a wave. Photons and light rays may be thought of as little bundles of waves emitted in a discrete packets, which call these packets as photons. Each packet behave like a particle and a wave is named as a photon. The luminous intensity, the symbol I, for light source is the luminous flux per unit solid angle, which we call steradian. So the luminous intensity is the luminous flux per steradian. A source having an intensity of 1 candela emits a flux of 1 lumen per steradian. The unit of luminous intensity is candela. The candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 times 10 to the power 12 Hz, and that has a radiant intensity in that direction 1/680 watt per steradian. Luminous flux is the energy per unit time that's radiated from a source over a visible wavelength. The unit of luminous flux is lumen. 1 lumen is equal to 1/680 watt of yellow-green light of wavelength 555 nanometer. In the previous page, we have said that the luminous intensity is equal to the luminous flux per steradian. When we take a light source with a light intensity I, it emits light in all directions. When we draw a sphere, these light rays illuminate the surface, and the number of these light rays is related to the luminous flux. So the solid angle of a sphere is equal to 4p, as light intensity is equal to flux over 4p. I have the formula of the luminous flux equal to 4p times I. This is the formula of the luminous flux for a whole sphere. Here we have 3 different spheres, and I put the light sources with equal light intensities at different locations. As flux is directly related to the light intensity, it is the same for all spheres, so they should have the same luminous flux. It is just related to the light intensity because 3 spheres is whole. In order for light to illuminate a surface, the rays should be perpendicular to the plane. So if it is not perpendicular, then the flux decreases. So you see here that at A is perpendicular, so it has the maximum flux. Here it is not perpendicular, so it is less. And here no rays is going through the area, no illumination, so no flux. The luminous flux is the energy emitted per unit time, so it is related to the power of the light or the light source. The luminous flux to power ratio determines the efficiency of the light source. So efficiency is equal to the luminous flux over the power of the light source. For example, a typical 100-watt incandescent bulb has a luminous flux of about 1,700 lumens. So its efficiency is equal to 1,700 over 100, which is equal to 17%. That means that 17% of the electric energy is converted into light energy. The illumination, the symbol E, of a surface A is defined as the luminous flux per unit area. This is the luminous flux in lumen. This is the area in meter square. So lumen per meter square give me the illumination, which has the unit of lux. So I know that flux is calculated by dot pi. The area of the surface of a sphere is 4πr squared. So illumination is equal to light intensity over the distance square. Illumination depends on the angle of incidence of the light rays. If the light ray is perpendicular to the surface, then I use the formula I over the distance square. If the light source has an angle alpha with the surface, then I use the formula I over the distance square times the cosine alpha. Now let's find the illumination at the points K and L here. Let's say this distance is X and this is Y. So illumination at K is equal to I over X squared. The illumination at L is equal to I over Y squared times the cosine 37 degree. We are going to find the ratio of the illumination of the light source at the point K at the points X and Y. Now the distance of the light source to X is 2 units. So illumination at X is equal to light intensity over 2 square 4. The perpendicular distance of K to Y is this distance, which is equal to root 2. So the illumination of Y is equal to intensity over root 2 square, which is equal to 2. So when we take the ratio, we find as 1 over 2. As illumination is inversely proportion to the distance square, as the distance increases, the illumination decreases. You see that it is for a point source. The distance is 1 and illumination is E. The distance is double, so illumination decreased by 1 over 4, which is equal to 2 square. The distance is triple, the illumination decreased by 1 over 9. But if the light rays are parallel, then the distance doesn't affect the illumination, because you see that the number of rays passing through each surface is the same. So in this example, the illumination E1 is equal to E2 and is equal to E3. Point light sources with equal light intensities I are put at the center of KL hemispheres and M spheres. Now we are going to find the relation between their luminous fluxes. the luminous flux is related to 4pi, the luminous intensity, for a whole sphere. But now here I have a hemisphere. So here the luminous flux will be equal to the half of it. Also here it will be equal to half of it because it is an hemisphere. But here I have a sphere, so it will be equal to 4pi. So the flux 3 will be bigger than 1, which is equal to 2. Now we use a photometer to measure the intensity of the light produced by an unknown source in terms of a standard source. We have a standard lamp here, which means that we know its light intensity, and this is an unknown light source. We put a screen here, it is translucent, and there's a grease spot here. If the illumination on both sides are equal, then I couldn't see the grease spot at the screen. So from this equalization, E1 is equal to E2, I can say, let's say this distance is D1 and this distance is D2. E1 is equal to I over D1 square, and E2 is equal to the unknown light intensity over D2 square. So I can find the light intensity of the unknown light source with this equation. Let's do an example. A 40 candela lamp. We have a light source from the candela and another lamp with an luminous intensity I2 are placed at the opposite sides of a Bunsen grease spot photometer. 40 candela lamp is 2 meters and the other is 4 meters away from the photometer. The light spot disappears. So what's the luminous intensity of the second source? So 40 over 2 square should be equal to I2 over 4 square. So I2 is equal to 40 times 16 over 4, which is equal to 160 candela.